Okay, maybe we can start now and then just let the others join in later. So again, good afternoon, Jehan and Francis. So welcome to week number 13 of the semester and meeting number 2 of the numerical differential equations chapter of AMAT 350. And before we proceed, just a heads up, I only scheduled the meeting until 5 p.m. today. Unfortunately, medyo may overlap dun sa schedule ko because I'm currently taking a postgraduate certificate in academic practice. Tapos ngayon natapat yung aming bi-weekly synchronous class. Tapos um, meron kaming peer-led seminar, so I need to be there. So kailangan kong i-cut short yung ating discussion. So we have some options. Either I'll give you a video recording of what to watch kasi malamang di natin matatapos yung mga modules natin ngayon, or we can extend our meeting on Thursday by 30 minutes para pambayad utang dun sa 30 minutes na mas maaga ko kayong i-dismiss today. So what do you prefer? Just a video recording na papanoorin nyo, or ano na lang tayo, extend na lang tayo on Thursday. Probably around from 4 to 6 p.m. tayo sa Thursday. Pero kung
Sir,
inconvenient... yes,
we have
Jehan, go.
class po, sir. We have class po on PBE. Kami po ni Ivy later. Mamaya po wala po kami pasok. Pero on Thursday, we have class po.
Okay, I see. So thank you for letting me know. Sige, ano na lang, magpapanood na lang ako ng video or bibilisan ko na lang sa Friday, sa Thursday. Because my goal is to finish the 2 modules that I gave you about numerical solutions to ordinary differential equations by Thursday. Para next week we can start talking about solutions to partial differential equation. But just a quick recap of what we did last time. We're talking about Euler's method. And we said that Euler's method is a very nice and simple way of providing a numerical solution to a partial differential equation. Sorry, not a partial, but an ordinary differential equation. Remember, we start with a problem in standard form dx dt equals f of xt over the interval or actually, I forgot which one we are writing first. Perhaps we're starting with the independent variable t first and then yung dependent variable x. And here is over an interval AB for our independent variable. And usually we have an initial condition, x of a to be equal to alpha, right? So ito yung mga klase ng differential equations na tinatry nating hanapan ng solution. So the first step in employing the methods that we'll talk about that we will talk about today, including Euler's method, which we started talking about last time, sulat niyo muna siya in standard form, okay? So dx over dt, and take note of whatever the function on the right-hand side is. So you have the derivative equals some function little f that will involve the dependent and the independent variable. Napaka-crucial yung tamang pagdetermine ng function little f, because that will serve as the major building block in our formula. Kasi gusto natin yung approximate natin sa solution sa ating ODE ay wala na sanang differentiation o wala nang fancy calculations yung kailangan. Actually, what we have seen is that Euler's method only require evaluation of the function value under the function little f. All right, so yun lang yung ginamit natin. Specifically, if you remember, this is Euler's formula that we have. So remember that the w sub i's are our approximates for x of t sub i's. So basically, after you write your solution in standard form, the next thing you'll do is to subdivide the interval AB into a set of discretization points, or what we call a mesh of points over the interval AB. So pili ka lang dyan. Usually we let it to be t sub 0. We let this to be t sub capital N. And then you can choose points t sub 1, t sub 2, t sub 3 until you get t sub n. So meron tayong n plus 1 points na gagamitin instead of considering the entire interval, because we are foreseeing the use of machines to compute our estimate for the actual solution to the differential equation. Now, what we will try to estimate to do is to pair the t sub i's with some function values or some estimates for the function values. Hence, instead of finding the exact value x of t sub 1, which we denoted by x sub I, which we denote by x sub 1, our goal is to estimate it by a number w sub 1 using only function values or function evaluation of the function little f. So if you have a one-step time marching algorithm, gusto mo na yung w sub I ay mako-compute mo using w sub 0 lamang. Right? And that's what Euler's method is offering us. It's a one-step forward algorithm of order 1. We'll see why it is of order 1 later, pero it's a one-step forward marching algorithm because we start at the initial condition w sub 0 and move forward to the right endpoint of the interval to get the w sub i's, w sub 1, and then w sub 2, w sub 3, and so on. And to find the value of w sub I plus 1, we're using only one previous estimate, namely w sub 1. And you see here, h sub I is just a step size times the function value under little f. So, unlaking simplification ang naganap dito. Kasi when we are computing the estimates w sub I plus 1, kailangan mo lang yung previous estimate which you have stored in the memory before, and one instance, one function evaluation of the function f, you will scale it by the step size, and you'll get w sub I plus 1. And then you continue the process moving forward until you get all of the w sub i's, all of your estimates for the x sub i's. All right. I think last time we stopped with we reached example 10.4 where we saw Euler's method in action, and then we compared the estimate that we got with the true solution. But here it's a very simple implementation because we're just in the interval 0 to 5, and I'm using the step size 0.5. So ilan lang to? I think it's 10 or 11 points yung nagamit natin. So medyo kakaunti yung discretization points na ginamit ko. Usually in practice, you want to have lots of discretization points because you will see that in the continuum, the error will vanish to 0 as a function of h, or as h goes to 0 as well. So gusto mong maliit si h, ang consequence, napakalaking mesh yung ginagawa mo. But just for the purpose of illustration, I use h equals 0.5. And then we got this table of w sub i's, and then we characterize also the relative error, which is basically the percentage error. I'm always dividing the absolute error by the magnitude of the one it's estimating para makita natin, magka-idea tayo gaano kalaki yung error relative dun sa gusto kong i-approximate. So you can think of this as percentage errors, but of course you cannot do this in real life because this will entail division by the absolute value of x sub I, actually subtraction din ng x sub I, and in real life you don't have access to these values kaya ka nga nag-approximate. Pero ito yung isang magandang practice. Whenever you're proposing a method, kahit sa mga models, meron tinatawag tayong validation step. So kapag meron kang method, or actually kahit isa lamang computer program that you design to simulate something, you want to benchmark it. You want to see how accurate it is. And since we don't usually have access to lots of hand solutions or exact solutions, hanap ka ng toy problem. Tapos yung toy problem na yun doon mo i-implement yung algorithm mo para lang magkaroon ka ng idea, is it working the way I intended it to be? Or kasi halimbawa yung Euler's method, mamaya sabihin ko it's a method of order 1. Using a benchmark test, an easy example, an easy OD, you can get a feel if the method is doing what it is supposed to do in the level of efficiency that you expected. So, lagi kang may benchmarking, tinetest mo siya with known values. At yun yung ginawa ko rito. So, kahit alam ko na yung actual x of t na solution dun sa differential equation, niran ko pa rin si Euler, tapos tinake note ko itong mga approximate, just to have an idea how good Euler's method is. And surprisingly, the method is quite accurate because the average relative error is about 4.62%, or if you want to be more mathematical about it, L2 relative error yung computed mo, it's 3.43%. And that's only And that estimate is only found by using function evaluations of f. So wala kang differential equations, wala kang calculus actually na ginawa. Function value evaluation lang yung ginamit mo, and you get an estimate that is within 3% of the actual solution. And of course, nobody's enticed by looking at table of values, so usually pinipresent mo yung data mo or your findings in a graphical form. Especially if it's a paper, people would like to read diagonally. Ano, tinitingnan lang nila yung pictures. So sa figure number 2, pinlot ko lang yung actual solution at saka yung interpolated plot ng t sub I comma w sub I na nakuha ko. And you see that, yeah, the two functions, the two curves are close to each other. And this is expected because we have already quantitatively described how good the approximation was. It's about 3.43%. And again, it's amazing because yung solution napaka-ikse. Kung bibilangin mo yung number of operations, ano lang siya? Isang addition, tapos isang multiplication, tapos function evaluation na ni F. So it's very computationally cheap. Ang dali niyang i-implement. Kahit nga sa spreadsheet, kahit nga manu-manuhin niyo yan, calculator, wag lang maraming discretization points, then you'll get a good estimate. Okay. Now we'll head on and look a little bit, so you can practice your understanding of this by implementing Euler's method, but with h equals 0.1. Actually, ginawa ko pala siya, hindi siya exercise, example pala siya. So, ano sa tingin niyo yung mangyayari when I replace h equals 0.5 by h equals 0.1 intuitively? Sige, what do you expect to happen? Kunwari, hindi nyo pa nabasa. Hopefully, hindi nyo pa nabasa. Para walang spoiler. So, what do you think will happen if I lessen h? Oy, tama na yung Netflix. Sagutin niyo yung tanong ko. Yes, Ivy. Tapos lumayas naman si Ivy. Sige na nga, Ben Paul.
Nag-present tapos di-disconnect ko.
Oo.
Hindi, sir.
Pinagbabawal na technique. Sure.
Hindi ako sumasagot kasi feeling ko baka hindi ito yung hinahanap nyo. Siyempre dahil mas malaki yung step size, so mas magiging onti yung entries dito.
Or baliktad.
Sir?
Or baliktad. Ang h natin kanina, 0.5.
Kala ko 0.05.
Mas kakaunti.
Liliit, so syempre mas dadami itong mga points na to.
Good.
Matagal yung computation and mas smooth siguro yung graph.
Okay, yeah, that's a good observation, and I think it's taking off from your observation last time, ano, na medyo hindi smooth yung nakuha natin na solution na interpolated, but hindi natin maisisisi kay Euler yung hindi pagiging smooth ng solution ka last meeting kasi si MATLAB yung nag-interpolate. So siya yung gumamit ng kanyang sariling algorithm to draw a plot, because all that Eulers afforded us is a set of discrete data points. And you're right, mas maliit yung step size, mas dense yung mesh. Mas marami tayong points na ginagamit. So if we do that, well, you can get actually, I think you'll get 51 data points instead of just 11 that we got last time. Tapos pag tinali mo yung relative errors nila, eto. Now, look at the average. On the average, the relative error is just 0.94%, and the L2 relative error is just about more than 0.5%, which is a big jump from the 3.43% L2 relative error that we have seen before. And this sort of makes sense kasi parang mas marami tayong ditong points na dinaanan. So whenever you have, parang intuition natin, no? Pag marami kang data na kinonsider, lagi kang malamang makakakuha ng mas magandang insights from that data. So here, we use a lot of discretization points, 5 times than before. So, in-expect na natin to. Yes, Ivy. Kasi mag-leave na naman yun. So,
sorry, sir, napindot ko kanina. Yung tanong ko, sir, ay, meron din bang stability yung Euler's method? I mean, kapag ka ba pinaliit natin ang pinaliit yung h, hindi kaya possible na parang mag-blow up siya or ano. Kasi ganun sa ano eh, sa finite difference.
Uh-huh. Oh yeah,
Meron
that's
kang,
that.
meron kang ano, parang ito dapat dapat hindi lalaki or liliit sa ganitong number yung step size mo para hindi para maging stable yung solution. Kasi
Yes, that's a good point.
Pinaliit yung H,
Mhm.
hindi stable yung solution mo. So meron din po bang ganun sa Euler's method?
Yes, meron din. Actually, yun yung isa nating tinitingnan. So hindi lang error analysis, pero pupunta rin tayo a little bit on stability analysis, especially the background here is looking at the bigger picture, after we do everything on paper, na dinerive natin yung Euler's method, we will see the theoretical error later. But sa susunod naman ay yung susunod na step, ipapagawa mo kasi to sa computers. At doon merong mga hanky-panky na nangyayari. Titingnan din natin yan later. So yeah, let's put a pin on that, Ivy. Pero you're right, there is some consideration. We cannot make H very, very small because some things will blow up eventually. Yes, Francis.
Yes, sir. Good afternoon. This is in connection with Ivy's question po. So, what is the advisable pala na value for H in this case? Is there...
Good question. Konting spoiler. It depends on the function little f. So, doon nakadepende siya lagi. Though, let's see. Pero makikita natin mamaya. May bibigay ang formula sa inyo that will relate the accuracy question and the stability question kanina ni Ivy para sa method na to. Kasi ang tanda ko yung on the top of my head, ang alam ko ay sa heat equation na threshold. Kaya lang PDE na yon na yung delta T over delta X squared must be less than 1/2. Hindi ko tanda sa Eulers. Kung mahaba yung formula, makikita natin later. But those are good points. Pero yun muna. Theoretically, yes. The more data, the better. The smaller H's, the better the approximation becomes. Pero tingnan natin kung bakit yun nangyayari. Pero siguro pakita ko muna yung picture just to convince you that indeed using a step size 0.1 gave us a more accurate solution. And this is expected because nakita natin yung L2 relative error noong nakuha nating solution nakuha nating estimate from the true solution is just a little over 0.5%. And that's evident here. Mukhang nag-overlap na yung dalawang graphs. Dito medyo nakita ko na, nung nag-zoom in ako, nakita ko na medyo naghihiwalay yung red at saka yung yellow. Pero the idea here is that they are almost overlapping, signaling that we are almost getting the exact solution. Almost, but not quite. Kasi meron pa rin silang mga disagreements along the lines. But yeah, another example, let me see what this example is all about. Okay. So this, I just used this example for the other function that we have, but I use this as a springboard to insert or to define what we call the global discretization error. So we see here, yeah. Oh, hold on. So how do you define yung GDRE? Okay. So I'll skip the next example. I'll just introduce the GDRE here. So meron dalawang klase ng errors. So before we go to the stability analysis that you mentioned earlier, tingnan muna natin yung error analysis. So meaning what are the sources of error in this scheme, which is the very heart of numerical analysis. So hindi lang tayo dito nag-apply ng methods, pero ina-analyze natin sila ano yung mga posibleng maging issues like what should be the optimal parameters, is there a bound to them, should they be big, should they be small, and so on. So unang titingnan natin ay yung sa error. Ano yung mga sources ng error? Una, yung tinatawag natin na global discretization error. I think I was going well ahead of myself there. Dinefine ko na pala siya dito kanina. Yung absolute difference between X sub I and W sub I is what we call the global discretization error. Right? So pag minus mo yung true solution mula dun sa estimated solution at t equals t sabay, yun yung global discretization error. Well, it might seem odd at first sight kung bakit siya tinawag na global. Local naman yung ginawa mo, nag-subtract ka ng x sabay minus w sabay. So your focus is on the specific t sub I. Ano? Pero this is global because you will see that in the very design of Euler's method, yung approximate mo para kay w sub I ay nakadepende dun sa estimate mo galing kay w sub I minus 1. So essentially, you're using an estimate, of course, other than the first step, which is basically based on the initial condition. But when t is greater than 0, you are using previous estimate, you're using previous estimate to get another estimate. So balikan natin to. Halimbawa, sa example na to, para makuha si w sub 2, so that means I is equal to 1, so w sub 2, kailangan ko si w sub 1. But w sub 1 is not the exact value x sub I. Yun yung nakita natin sa derivation ni Taylor ng Euler's method. Dapat ito ay x sub I plus h f prime f of t sub I comma x sub I. But we don't have access to x sub I. That's why we replace x sub I by w sub I. But w sub I on itself is just an estimate. And you're feeding the algorithm with a previous estimate to get another estimate. So that means the error, the absolute difference between w sub I plus 1 and x sub I plus 1 is not just the error incurred on the particular step t equals t sub I plus 1, but essentially it accumulates, all right? It represents the accumulated errors from the previous estimates. Kasi nadadamay si w sub I plus 1 dun sa error na nanggaling kay w sub I. Pero si w sub I, kinompute mo yan gamit yung estimate na w sub I minus 1, which is already tainted by some errors. So essentially, merong mga fractions ng errors mula dun sa previous steps in the solution ang nasasama doon sa error kay w sub I plus 1. So that means that's why we call it the global discretization error. Kasi accumulation na siya ng mga errors from the previous time steps until now. And with that in mind, parang inisip natin, there should be an increasing trend in a global discretization error. So basically, ito yung nagre-represent ng GDE. But this is relative error. So let's call it the global discretization relative error, right? Or the GDRE. We're expecting an increasing trend in the GDRE kasi nag-accumulate sana or nag-accumulate daw yung error. So nagpa-pile up sila supposedly sa padulo. Kaya dito papasok din yung question kanina ni Ivy na kapag ka masyadong maliit si H, marami nga yung mesh points, pero dahil forward algorithm to, ibig sabihin para makakuha ka ng estimate kay x of b, which is your right endpoint, dumaan ka na sa napakaraming mga estimates. So mag-accumulate dapat yung mga discretization errors doon. So pag nakarating ka na kay x of b, makuha mo si w of t w sub capital M, nandun na. Dapat mas malaki yung error kasi nga nag-accumulate na. But thankfully, hindi lang kasi one directional yung errors. Minsan positive yung error, minsan negative yung error, and if you're lucky enough, most of them will cancel each other out or will almost cancel each other out. So I guess that's one possible explanation why there is no increasing trend. Pero in-expect na natin yon. There should be an increasing trend if you will be taking the absolute errors every step of the way. Pero dahil nagka-cancel yung mga artifacts na yon, posibleng hindi increasing yung trend. Okay? Dun sa error. Pero usually magandang benchmark ng accuracy ay ano yung nangyari dun sa final, dun sa right endpoint. How accurate is the right endpoint? Nakasurvive ba siya dun sa global discretization relative error or the accumulation of the errors from previous time steps. Okay? So that's GDRE, but there's another source of error. This is more on the GDRE is more on the implementation stage na. But on the actual derivation, sa simula pa lang, nung pagde-derive natin ng error, meron na tayo, nung method, meron na kagad tayong na-introduce na error. And that is what we call the local truncation error. The local truncation error is the error incurred when we replaced the continuum problem, which is in this case taking the derivative by a discrete approximate. which is the divided difference, right? So essentially, if you remember, our problem is, dito na lang. Our problem initially is dx over dt equals f of x, f of t comma x. And then we said we will replace dx over dt by a discrete analog version, a discrete version, because computers cannot handle derivatives because it's a continuous operation. So we will replace dx over dt by w sub I plus by x sub I plus 1 minus x sub I over h sub I, all right? And then the right-hand side will be transformed in one way or the other to a function phi that depends on f, the h sub i's, the t sub i's, and the x sub i's. So the mere fact na sinimulan natin yung method by replacing the continuum operator by a discrete one, meron na tayong na-incur na error. And that error is what we call the local discretization error, or the local truncation error rather. It's afforded the name truncation dahil dun sa truncation ng Taylor series expansion, right? So for instance, in Euler's method, okay, ito yung actual expansion, o ito yung makukuha, this is the actual expansion using Taylor's theorem. The equality is preserved because I kept the second derivative term, but instead of evaluating it around t sub I, pinalitan ko siya by an arbitrary number, by a number c, by an unknown constant c, which leaves between t sub I and t sub I plus 1. So eksakto pa rin yan. Natanggal ko na yung manatitirang errors. But if we want to look at or to quantify the local discretization, the local truncation error, titingnan natin from this exact expression. Ano yung value natin para kay x sub I plus 1 minus x sub I all over h sub I. Kasi yun theoretically dapat yung magiging expression natin para dun sa right-hand side. Okay. But essentially, if you do that, you will see here that x sub I plus 1 minus x sub I all over h sub I will be equal to f of t sub I comma x sub I plus 1/2 h squared x double prime of c. So ito yung pinampapalit natin kay derivative, kay dx over dt. But we know that dx over dt is equal to f of tx. Galing dun sa problem. Sorry, magulo talaga ako. Kaya minsan ayoko nang may module na ginagamit. Mas maganda yung free-flowing. But I hope you can still discern what's happening on the screen, right? So see, x sub I plus 1 minus x sub I over h sub I, pinalitan ko siya, or siya yung pinampalit ko sa derivative. Yes, Benpo.
Sir, wala bang h sub I dapat yung denominator ng second term?
Denominator ng second term.
Yeah,
thank you. Yep. Kasi hindi nga pala tayo uniform step size. All right, thank you. So yeah, we're replacing the derivative by this divided difference, and this and then the derivative from the problem itself is equal to f of t comma x. So when you evaluate the derivative at t sub I comma x sub I, dapat magmamatch yung dalawa. If you take the difference between them, that's what we call the local truncation error, and we denote it by by tau sub I, right? So essentially, kunin mo yung difference, f of t sub I comma x sub I minus this guy, what will be left would be h squared sub I over 2 times the second derivative evaluated at the number c. And hence what you see over here. H squared over h sub I dapat.
Sir, kasi divide by h sub I lahat ng terms. So itong last term, maka h squared over h sub I dapat. Tama ba?
Or gawin ko siyang h sub I lahat para ma-cancel.
Pwede rin sir pag ganun.
Yeah. So ganito na lang.
Yes, sir.
Yeah. Medyo ang gulo ko rito nung sinusulat ko to. Hindi ko
okay, sir.
Yeah. Hindi ko malaman kung gusto kong uniform step size. So gusto kong general na iba-iba yung step sizes. Ano? So pero yun. Thank you for those corrections. Kaya hindi ko pa ito ina-encode. So dapat matest pa yung module. But essentially, that's the local truncation error. And I don't know if you guys have encountered the big O notations, the Bachmann-Landau notations, when we want to just look at the order of quantities or numbers, either with respect to infinity or with respect to zero. So, ang ginagawa natin doon ay dinadrop natin yung mga insignificant terms. Pero in this case naman, isang term lang yung natira rito. So that's fine, wala tayong itatruncate. Kasi kung mahabang summation yan, kalimutan mo na yung konti lang yung ambag. Doon ka lang mag-focus kasi tinitingnan mo lang in the ballpark yung number. Tinitest mo along what number or what order yung quantity ay involved. Para lang hindi mo i-keep track yung mga unnecessary details like insignificant terms. Right? So yun yung una sa Bachmann-Landau notations. Pwede mong i-drop yung mga lower order terms. And then, you can drop constants. Kasi tinitingnan mo lang naman ay usually pagbabago with respect to one of the variables. So if I will assume that the I don't have any way to compute C sub I, which is always the case, but this is just a constant anyway, so it doesn't matter when I look at the asymptotics of it. So basically, you can just say that the local truncation error is of order big O of H sub I. All right? Tanggalin mo lang yung mga insignificant terms, tanggalin mo lamang yung mga unnecessary constants or scaling constants. Just focus on the important factor, the determining factor in this truncation error. Right? So the big O notation is basically, it gives us an asymptotic upper bound. So meaning that our function, the exact expression, will be eventually bounded above by a scalar multiple of the function h sub I, or the function h. Kaya yung Eulers method, tinatawag natin siya na order 1. Kasi ang order ng local truncation error niya ay big O of h. Now, in the infinitesimal sense, when h becomes very, very close to 0, so you can interpret the big O notation or the order of a method by the error vanishing as fast as how the thing inside the big O approaches 0. So kung yung Eulers method, sinabi natin siya ay order big O of h, ibig sabihin yung error ay nag-approach ng 0 kasing bilis ng pagze-0 ni h. That's how you interpret yung big O infinitesimal asymptotics in the context of problems like these, right? So that's why nakita natin yung trend kanina. I-justify niya yung nakita nating behavior when we reduced the value of h from 0.5 down to 0.1. Nakita natin from 3.43% to 0.68% GDRE, lumiit na yung error. Okay? Doon kasi, hindi ko pala dapat technically tinawag. Sa GDRE kasi, factored in na rin yung local truncation error. Tama, no? Kasi na-implement ko na yung method, tapos nag-accumulate lang siya. So yung accumulation ng mga local truncation errors, sila yung nagko-contribute para makuha yung global discretization error. So kaya sama-sama na sila doon. So the order of the method incorporates both of them. All right? So sa global discretization error, kasama na yung local truncation error, which you can think of as the theoretical error involved in the method itself. So at least on theory, kapag ka si h ay pinaliit mo, mag-approach kay 0 yung ating error as fast as how h approaches 0. Yun yung ibig sabihin ng big O of h. So kung yung error ay kinalahati mo, then most likely around kalahati rin yung makukuha mo, or actually scaled pala, no? It's a factor of 1/2 yung mababawas dun sa error. Ganun yung kanilang parang proportionality. All right? And so nakita natin na that is actually exhibited by the two examples when we varied the step size. Right? So it's a method of order big O of h. Pero let's see some more details here. Kasi pupunta ako dun sa question ni Ivy kanina na, is there a limit? Kasi in theory, on paper, kapag ka ginawa mo yung Eulers method, mag-approach ng 0 yung local truncation error kapag ka si H pina-approach ko ng 0. So that means a denser mesh, the better. Okay? Tapos, dahil lumiliit yung local truncation error, dun sa bawat approximation na ginawa ko, lumiliit yung error. So sa bawat step ng pagko-compute ng W sub I, yung inherent error galing dun sa approximation ng derivative by the divided difference ay lumiliit. Ang effect niya, yung GDRE o yung GDE ay lumiliit din. Kasi nag-accumulate lang naman sa GDE ay yung mga local truncation errors sa bawat sa previous time steps. So pag lumiliit yung LTEs all throughout the interval, lumiliit din yung GDRE all throughout the interval. Okay? And on paper, the order of Taylor's method suggests that we make H approach 0. But we will see that that's not always the case. And let's try to trace why. Now, an important thing is, I think you already know this, so I'll just mention it in passing. If condition 10.12 is satisfied, then we say that the function f is Lipschitz in the dependent variable x and independent variable t. So kapag ka yung relative, yung change dun sa function values ay bounded above by a constant times the relative by the absolute change in the x's, then Lipschitz continuous yung ating function. And the constant L here, or actually not the constant L, but the least upper bound siguro. Least upper bound, supremum, least upper bound. Yeah, the minimum value for L, that's what we usually refer to as the Lipschitz constant. All right? Pero yung ibang authors, basta nakahanap ka ng L na totoo yung equation 10.12, tinatawag na nila ng Lipschitz constant si L. But still others would like to call L the Lipschitz constant. So siya yung pinakamaliit na posibleng L. Pero dito, para safe, ayoko kasi maghanap pa ng mas maliit na L. So tinawag ko siyang a Lipschitz constant. So there are infinitely many Lipschitz constants, but usually we want the smallest possible Lipschitz constant. But anyway, all that equation 10.12 tells us that the relative change between function values are bounded above by the constant. There's no sudden blow up of the relative changes between function values. So yun lang yung sinasabi ng equation 10.12. Control yung increasing behavior or decreasing behavior ni function f. Now, it's quite hard to always go by the definition to check Lipschitz continuity. Well, this is an alternative way. This is, I think, a sufficient condition for Lipschitz continuity. Kapag ka bounded yung partial derivative ni f with respect to the independent variable t by some constant L, then we say that the function is Lipschitz in the dependent variable x on the domain D. Okay? So kunin nyo lang yung partial with respect to t, mache-check nyo na kung siya ay Lipschitz continuous. All of this work is targeted or are targeted para makuha ko yung upper bound para sa global discretization error. We already have an idea of how big the local truncation error is. But actually, hindi lang natin concern yung local truncation error kasi nga nag-accumulate pa sila hanggang sa dulo. And that might affect yung quality ng ating approximation kasi sila yung nag-accumulate. So pag sobrang liit ni H, sobrang daming points ang kailangan daanan mo para makarating ka mula kay A, para mapunta ka kay B. So baka naman mag-add, hindi mag-cancel yung mga LTIs. So lalaki yung global discretization error. Now, the Lipschitz constant and the fact that the partial derivative of f is bounded above and the partial derivative of f will be shown later to be directly related to the second derivative of f of x, may makukuha tayong upper bound para sa global discretization error. Well, there are some theorems here that tells us ano yung implications ng pagiging Lipschitz aside from having a Lipschitz constant that will play a big role in the upper bound that we will have later. Yung pagiging Lipschitz continuous, medyo ano rin siya. Magandang idea siya para dun sa well-posedness ng isang problem. Well-posedness is very important because well-posedness tells us that the solution can be found, it is unique, and it is stable. All right? Medyo misleading to ng konti kasi parang in theorem number 12, parang ang dating niya, as long as Lipschitz continuous yung right-hand side nung ODE mo, yung function f, lagi daw siyang well-posed. ano ba yung konsepto ng well-posedness? According to Hadamard, gamitin natin yung Hadamard definition ng well-posedness. Una, well-posed ang isang problem even only if it satisfies two conditions. Number one, there exists a unique solution. So yung pala, Lipschitz continuity guarantees the existence of a unique solution. Hindi lang existence ng solution, pero uniqueness ng solution. Second, para maging well-posed ang isang problem, dapat the solution depends continuously on the data. So if the problem will vary by a little bit, may konting percentage variation in the problem, say instead of x prime equals f, naging ano to, x prime equals f of xt plus some function epsilon of xt, where the L2 norm of epsilon is very, very small, yung solution from the epsilon problem should be very, very close to the solution of the original problem. Yun yung ibig sabihin na yung solution ay nagdedepende continuously dun sa data. A small perturbation in the data, in this case, our data is our right-hand side, maliit na pagbabago dun sa data, dapat maliit lang yung pagbabago sa solution. And Lipschitz continuity guarantees that for the ODEs of this form, we're laging well-posed. So you might be thinking, kung well-posed yan, so dapat wala akong maging problema. Dapat kapag ka si H ay super liit, dapat liliit din yung error. Pero ito dapat yung nangyayari on paper. Pero meron pa tayong isang component na ginagalawan dito sa konteksto ng Eulers, ng implementation natin ng Eulers method. Hindi natin to ginagawa on paper. But again, I'm going off script. Parang meron pa akong isang gustong sabihin. Hold on. Oh, there we go. This is what I want to see. Theorem 10.3. Ito yung nagbibigay sa atin ng upper bound para dun sa global discretization error ng Eulers method. Now here, we require f to be Lipschitz on Lipschitz in x. So dahil siya ay Lipschitz in x, okay, meron siyang Lipschitz constant. You can pick your Lipschitz constant, but the lower the Lipschitz constant is, the better, because the tighter bound yung makukuha mo. And there exists an m, and if you can find an upper bound for the second derivative of x over the closed interval of consideration, okay, then yung global discretization error is bounded above by hm over 2l times this guy, e to the l times t sub I minus a minus 1. So ito na yung parang quantification natin para dun sa error. Sure tayo na in the worst case, the error, the global discretization error for every I will just be around this number. Okay? And again, yung initial hint ko kanina na ayaw paniwalaan ni Ivy, dapat si H paliitin ko lang ng paliitin, ano? Ano pa rin, nasusustain pa rin ang theorem 10.3 na, nga, kapag ka si H ay pina-approach ko ng 0, ibig sabihin, itong GDE ay bounded by a very small number. And so that means the absolute value of yi minus w sub I will be approaching 0. Okay. And again, this also tells us that the order of the local truncation error of Euler's method is inherited by the global discretization error, because all of these guys are just constants, right? So still, the GDE is a big O of H. The faster H goes to 0, the faster your error will go to 0. Kasi magkasing bilis si H nagsi-0 at saka yung absolute value ni y sub I minus w sub I. Okay. Pero syempre, tama si Ivy dun sa sinabi niya kanina na hindi laging dapat paliitin mo lang si H. In theory, yes, the smaller the H value, the better. Kaya lang hindi yun yung nangyayari. Bakit? Kasi meron pang isang layer yung ginawa nating implementation ng Euler. Dinerive natin sa papel yung Euler, which is fine. It's a big O of H method, order 1 method. Pero in-encode ko siya sa MATLAB. Pinakompute ko siya kay computer para i-solve yung problem. So siguro merong kasing dalawang perspectives yung tanong ni Ivy kanina about the stability. Merong theoretical stability na tinatawag din, pero kakibat yun ng well-posedness, right? Pero yeah, Kapag ka hindi well-posed yung problem or hindi well-conditioned yung parameters o yung model mo para dun sa solution mo, kahit ano pang gawin mo, hindi ka makakakuha ng stable solution. Okay? Kasi inherently ill-posed yung problem, hindi nagde-depend continuously sa data yung solution. Alright? And usually, wala ka na dong further consideration because we always want to look at stable problems. Pero ang problema rito ay tinanggal ko na yung perspective na yon. So, may mga stability conditions na kailangan para masabi na hanggang ganito yung value ni H. Pero dito sa kinonsider natin na Euler method, nag-start kasi ako ng assumption na I see Fi Lipschitz. This is sort of the ideal, the most ideal or close to ideal scenario, that the problem itself is well-posed. Lipschitz na siya, so well-posed na yung aking problem. So I should not worry about H being very, very small, having a big impact on the solution, or the error will blow up kasi sobrang liit ni H, kasi inassume ko na kagad na si Fi Lipschitz. Alright? Pag si Fi Lipschitz, guaranteed na well-posed yung problem. Kaya lang, hindi pa rin ganun yung nangyari. Or kahit na nasa ideal scenario ka na Lipschitz yung iyong problem, you still need to be extra careful because you will be asking a computer, which is a finite machine, to perform the calculations with you. And inside the computers, hindi niya pina-perform yung solutions, yung operations exactly. Number one, dun pa lang sa storage ng mga numbers. If you have an irrational number, ikakat yan ni computer to its finite floating point arithmetic alphabet. Right? So limited lang yung number of numbers na kaya niyang basahin. Hindi ko na sasabihin kasi wala na akong oras. Meron kasing tinatawag na F of, merong set. Actually, kaya nating bilangin yung ilan lang yung mga numbers, distinct numbers, yung nasa loob ng ating computer. So if you have a number that you need to involve in your computations that is not within that alphabet of numbers dun sa isang computer, then ita-truncate niya yan. Pipiliin niya yung pinakamalapit na representative, the floating point representative for a number. And then, pangalawa, after every operation, nagta-truncate yung computers. So, halimbawa, double precision arithmetic, 16 significant digits lang yung kanyang nire-retain. So, kapag meron kang 16 significant digits na nako-consider lang after every operation, it makes sense that you don't want your H to be smaller than 10 to the minus 16. Kasi kapag yung H mo ay lampas na ng machine precision, ibig sabihin, halimbawa, si H mo ay 10 to the minus 18, yung machine precision delta mo ay 10 to the minus 16, ibig sabihin, yung yung F of T sub I, X sub I, at saka yung F sub T sub I plus 1, X sub I plus 1, ay posibleng basahin ni computer to be the same numbers. Kasi guys, T sub I minus T sub I plus 1 will be very close to each other. And virtually, iisipin ni computer that they are the same. Kasi nga kung ang machine epsilon niya lang ay 10 to the negative 16, ay yung step size mo ay 10 to the negative 18, ibig sabihin nun, kapag yung difference between two numbers ay within 10 to the minus 16, lagi lang siyang virtually kinoconsider ni computer to be one and the same number. So kapag itong dalawa ay equal, then most probably, since our solution X depends continuously on T sub I, when the derivative of X is very small or is manageable, then the X sub I's and X sub I plus 1 might be very similar to each other. Kamalas-malasan mo kapag within 10 to the minus 16 then, or smaller than 10 to the minus 16 yung error. So essentially, etong dalawang numbers na to, i-consider ni computer to be the same. And hence, you are committing a cancellation error. So there are two very close numbers na pag pina-minus natin kay computer, iniisip ni computer 0 na yung sagot. So that's one reason why we don't want H to be very, very small, even though we know that the problem is well-posed already. Wala na dapat tayong issue about the choice of H as long as F is Lipschitz continuous. But that's on paper. Once you put it into the computer, we need to take care of, or we need to consider the machine epsilon. And for that, I guess I have a theorem here. I need to skip some of the meaty parts of this handout, specifically this pages, probably this paragraph could be of interest to you. So yung paragraph na may 10.13, right? Or the after theorem 10.3, kindly read that passage because you might get some insights from it. I don't have time to go through that. So, punta na ako dun sa theorem. Theorem 10.4. Okay. Yung theorem 10.4, specifically equation 10.17 below here, gives us an idea what is the global discretization error, but this time we are considering machine precision. Okay? Kasi nga, halimbawa, ito yung problem mo eh. So ideally, ang initial condition mo dapat W sub 0 equals alpha. Ito yung initial condition natin, no? Pero dahil walang kasiguraduhan na yung pagbasa ni computer kay alpha ay eksaktong alpha, hindi ko nakukuha yung tamang W sub 0. Ang nakukuha ko ay si U sub 0. So this is the machine. This is from the machine's perspective or the machine's point of view. Ito yung ginagawa ni machine. Yung initial condition dun sa ating Euler iteration ay U sub 0 ko tinawag kasi hindi siya yung eksaktong alpha. Si alpha ay co-convert dun sa kanyang floating point representative. So it could be written as alpha plus delta sub 0. Delta sub 0 is what we call the truncation error, or the machine truncation error, just to distinguish it with the LTE we discussed earlier. So yung machine truncation error, yung na-chop off dun sa rounding o dun sa chopping arithmetic na ginamit mo. Kasi hindi eksaktong alpha posible yung masave. Ang save ni computer ay alpha plus some delta sub 0 that canceled some of the unwanted significant digits. Tapos, pag kinumpute mo na yung U sub I plus 1, meron ka uli diyang truncation error na involved. Of course, may na-inherit din dito somewhere, but let's just consider it to be lumped together with delta sub I. Okay. So pag kinonsider mo na yung machine epsilon or the machine precision, let's say that all of the truncation errors, the machine truncation errors, is bounded above in magnitude by delta, and usually we call delta the machine epsilon or the machine precision. Ano? So yung total error ngayon, yung global discretization error, dun sa machine implementation ng Eulers method ay equal dito sa expression sa 10.15. Actually, the proof is not hard, though I usually skip this kasi ano siya, tedious arithmetic yung kailangan. Dapat matyaga ka dun sa pag-keep track ng mga global, ng mga truncation errors. And then you will sum them up. You'll use triangle inequality a little bit. But I think you can pull up a proof of this theorem online. It's I think it's straightforward. You can read it. Pero yun nga, medyo mahaba yung isusulat nyo doon. Pero just a sanity check sa equation 10.15, when delta is equal to 0, meaning your computer is perfect, it's finite, it's infinite, wala siyang truncation error, makita nyo that this reduces back to the global discretization error or the upper bound we have for the GDE. Kasi mawawala ito. So it's back to HM over 2L times this exponential minus 1, the GDE. Pero pag inimplement mo na siya sa computer, wala na. Kahit yung maliit na delta, kahit super liit ni delta, pag maliit si delta, maliit yung machine epsilon, ibig sabihin napaka-accurate ng floating point arithmetic at ng floating point representation dun sa computer. But even if delta is very, very small, you will see that ang laki pa rin nagiging epekto nung machine precision doon sa actual error because of the term delta over H. Well, of course, this is a constant, so you can just leave it for now. Let's focus on this term. Well, this is a constant that you can compute, so it doesn't matter too much. 1 over L, it's a constant. It doesn't matter too much. So the focus in the analysis of equation 10.15 should rest upon this factor. H over M over 2 plus delta over H. Again, in a perfect machine, it is just HM over 2, which backs up our conclusion earlier that in the Eulers method, as H approaches 0, the error vanishes. But now we have machine precision to also consider. And machine precision introduces an additional term here, delta over H. And now when you take the limit as H approaches 0, this guy can blow up to positive infinity. Ito yung isa dun sa mga, ito yung isang posibleng interpretation sa question ni Ivy at saka ni Francis kanina, na baka naman merong threshold yung value ni H. Alright? When you choose H to be very, very small, you're really making the contributions of the local truncation error or the global discretization error to a minimum. Lumiliit yung error, yung theoretical error. Kaya lang dahil sa computer natin pinagawa yung computations, merong nadadagdag na factor ng delta over H. Pero delta over H will approach 0 when H approaches 0. So magkikick in yung machine error or yung machine truncation error whenever H is very, very small. On the other hand, if you choose H to be very, very big, ang unti lamang nung nagiging contribution ng machine truncation error, pero ang laki naman ng theoretical error. So you need to find the perfect balance between these two guys. All right. Now to answer Francis's question kanina, what's the best H? Hindi ko siya binigay dito, pero kayang-kaya niyong i-derive using your basic calculus prowess. Treat this as a function of H, and then you minimize this number. So you find the minimizer, minimize H of this expression here, you will find the optimal step size H. The perfect balance or the perfect compromise between the theoretical error quantified by the global discretization error and the machine truncation error. So hanapin niyo yung optimal H para dito. All right. So minimize nyo lang to. First derivative test lang, get the critical numbers, then first o kaya second derivative test, you'll find the best H. Because I think all others here are constants. Yeah, all other here are constants. Okay, so I guess that's it. As I mentioned kanina, but some of you might have missed it, I cannot attend the meeting until 5:30 today kasi I'm taking another online course ngayon with University of Liverpool. Medyo odd nga kasi hapon yung aming seminar. Ngayon yung aming bi-weekly seminar starts at 5 and I need to present something there. So kailangan ko i-cut short. I apologize for that. Possibly mangyayari pa to sa Tuesday week after next kasi bi-weekly yung aming meeting. And then since I think some of you have AMAT 152 or MAT 252 after 5:30 ano. So hindi ako pwedeng magbayad utang ng additional 30 minutes on Friday. So what we'll do is on Friday, on Thursday, I'll discuss the next module, the other module, which is about alternatives to Euler's method for 1.5 hours. Then kung ano yung hindi ko matatapos, bibigyan ko na lang kayo ng video na papanoorin para makompleto yung picture nitong mini course on ordinary differential equations. Of course, there are lots of other methods para numerically isolve ang isang ODE. Pero ito yung mga classical, ito yung mga basic. There are more fancier and more complicated methods. Pero since we have done a deep dive for Euler's method, you can replicate what we did when you analyze Taylor's method, or when you analyze the Runge-Kutta methods, or pag may na-encounter kayo later na methods, kaya nyo nang tingnan. Kasi ganito lang naman lagi yung templates. You look at the global discretization error, you look at the local truncation error, plus you look at the effect of machine epsilon to your solution. Because after all, we'll be using computers to do the job for us. Ano? So yeah, I think that's it. Do you guys have some burning questions? While you're thinking, another suggestion is kindly read through the rest of the module. Ang dami kong in-skip, or hindi pala marami, OA naman. May mga in-skip ako that I think are some insightful points na medyo kailangan kong pigilan yung sarili ko na i-discuss siya kasi dadaldal na naman ako ng marami pag sinimulan ko. So para matapos ko tong module na to for today. Okay? Any burning questions na hindi nyo kayang patulugin at antayan na i-email sa akin? Okay, so if there are none, guys, so again, early dismissal tayo today. Thank you for joining me today. I appreciate the discussion. You are participating actively. Hopefully, ganito tayo palagi para hindi lang ako yung nagmo-monologue dito. And let's see each other again on Thursday, okay? Bye, guys.
Bye, sir. Thank you.
Thank you.
All right.
Thank you,
Bye-bye.
sir.